Now let's resume our discussion on series, and let's review this briefly along the way. We talked about what a series is, we talked about partial sum concept, and then convergence and divergence. We talked about this nth term test for divergence. Please remember to use this for divergence. It doesn't work for convergence. Such as something like this. The general term is 1 over n. That goes to 0. However, the original series diverges to infinity. Geometric series is very important object, and the geometric series formula is very important. And it goes like this: a over 1 minus r when r is less than 1 in absolute value. When r is greater than or equal to 1 in absolute value, we must have a divergence due to the nth term test for divergence. And then next we have to discuss telescoping series, which is relatively less important compared with geometric series formula, but nonetheless this is one of the rare example of series that we can actually calculate. And I've written telescoping series problems not every semester. I taught calculus too. Some semesters I did, some semesters I didn't. I don't know what I'll do this time. Depending upon how things will go, I'll make a decision. And let's go over to an example problem. And here's one such example. I lost a track. Yes, here. Typical typical telescoping series problem. How do I tell? Denominator is quadratic trinomial that can be factored. Especially it can be factored as monic trinomial. That's easy. Non-monic, that's a bit difficult. Monic case is much easier because it's easier to decompose it by partial fraction, and we have something like this in this particular case. 2 over n squared plus 4n plus 3. So the first step is to factor the denominator, and then you can set up a appropriate equation or something to decompose it by partial fraction like this. 1 over n plus 1 minus 1 over n plus 3. And after that you can write first several terms. Plug in n equals 1, we have 1/2, and then plug in n equals 1, we have minus 1/4, 1/3 minus 1/5, and so on. And soon you're going to see cancellation. This 1/2 will survive actually. This 1/3 will survive. This minus 1/4 and that 1/4 will cancel each other out. This minus 1/5 and that 1/5 will cancel each other out. This 1/6 and the next 1/6 will cancel each other out. Everything will go out. In the end, what do we get? Only the first two terms will survive. The answer is 5/6. Actually, how do I know first two terms will survive? We can tell by the difference. N plus 1 and n plus 3 differs by just 2. So what do we have? Just 2 terms. If we have n plus 1 and n plus 4, then you'll have to use first 3 terms. Of course, if you write many terms, then you'll see patterns. What if you have something like this? Factor n out and then n plus 3. The difference is 3, so first 3 terms will survive. The detail is left to the students. Okay, we talked about telescoping series, which is relatively less important. Let's go back to geometric series this time, but with undetermined number or some variable x. These kind of series are actually called power series. As a matter of fact, this one down here is not a power series because the power is in denominator, and this kind of thing is called Laurent series after French mathematician Laurent. Kind of goes like this. The common factor for this term, for example, what is the common factor that is keep being multiplied? What is the r value? R value in this case is x minus 4. And you need R value to be less than 1 in absolute value. So this is what we get. meaning -1, x minus 4, 1. So flipping 4 to the other side, we get, and that's when we have convergence. So this is the condition for convergence. So find the values of x for which the series converges. Oh, I don't like this term very much. I took this from our textbook, but it looks like we have just single x value. As a matter of fact, we have an interval. If I say find the condition for which the series convergence, then that'll intimidate students too much. Find an interval, then that could be misleading in some case. I don't know what to do. Find the values for which the textbook's explanation does its job, but please be warned, don't be misled by this. X doesn't have to be a single value. X equals to something. Just like you saw, you have to expect an interval. And then we have to find out the sum. Well, once you have it, sum is easy. What is this geometric series formula? This is it. So our value is x minus 4. Good. And what is the a value? What is the starting value? Plug in n equals to 1. Then we have x minus 4 as the starting value. So that is your s value. And if you want to simplify it, you're going to get x minus 4 over 5 minus x, it appears. Did I do this right? Yes, okay. How about the third problem? In this case, our value that is keeping multiplied is going to be 2 over x minus 3. Both of them have n power, so that's it. So that has to be less than 1 in absolute value. So what do you get? -1, 2 over x minus 3, less than 1. So, well, okay, from this point on, I'll have to leave you here, because in order to flip this inequality, you have to multiply by denominator. And denominator is a little bit different this time, because x minus 3 can be either positive or negative. So you have to work a little bit hard to find out. And then how about the sum? You can use the geometric series formula, of course. A over 1 minus r. R value is 2 over x minus 3. Good. What is a value? You can find out by plugging in n equals to 1 to this expression. The detail is left to the students. Let's see, what do I have here? Do I have the answer there? Okay, we are supposed to have 2 intervals. Okay. And alright, that's where I'm going to stop. Now, let's move on to the final topic that I left behind, the proof that harmonic series diverges. And the reason why I left it behind is because it's a bit too advanced for general public. So let's talk about it. The main idea is to do some underestimation, and that's not easy to see. Here it is. Here's the harmonic series, 1 plus 1/2 plus 1/3 plus and so on. And now we do something mysterious. We just group this series up to now 1/2, and then up to 1/4, 2 numbers, up to 1/8, we have 4 numbers, up to 1/16, you have 8 numbers, up to 1/32, we have 16 numbers, and so on. In general, you group 2 to the certain power, to be more precise, 2 to the n minus first power of numbers in a group, where the smallest number is 2 to the 1 over 2 to the nth power. In this particular case, the smallest number here is 1/8, 1 over 2 to the third power, and then we are grouping 4 numbers, 2 to the second power. And then what we do, we take underestimation. We underestimate entire group by replacing everything by the smallest number. So 1/5, 1/6, 1/7 are all replaced by 1/8. So what do we have? We have an underestimation. Down below is smaller than the top. And the same thing for a previous group. And does it make our estimation simpler? Yes, indeed. The first one, we don't really meddle with it, 1. And the next, 1, 1/2. And then we have 2, 1/4. We have 4, 1/8. And it will have 8, 1/16. And we'll have 16, 1/32. So what do we get? 2 to the 0 power times 1/2 to the first power. 2 to the first power times 1/2 to the second power. 2 to the third power, 1/2 to the third power. And so on. 2 to the third power, 1/2 to the fourth power. 2 to the fourth power, 1/2 to the fifth power, and so on. Everything will be just 1/2, 1/2, another 1/2, another 1/2, and so on. So what if you add, excuse me, what if you add the same number infinitely many times? You have to have an infinity. Conclusion, this series is still infinity after underestimation. So that must be going to infinity too. And that concludes the proof, actually. A little bit more detailed explanation. Well, we have to deal with partial sums to be a little bit more precise, but I'm gonna leave you here. The main idea is appropriate grouping. 4 numbers of 4 fractions where smallest is 1/8. In general, 2 to the n minus first number where the smallest is 1/2 to the nth power, so that you get just 1/2 every single time after underestimation. That is the key technique here. If you didn't understand the key technique, well, that's okay. This may not be for everybody, but still, everybody must remember the result. Harmonic series diverges, and that serves as a counterexample that the converse of theorem 2.2 does not work. Limit of the general term going down to 0 does not imply the original series converges. No. And the reason for that no is given in the next example.